All right, here we go. So we're going to finish up glycolysis and then tell you how pyruvate becomes acetyl-CoA today. I will probably get to some of the citric acid cycle today, maybe. If not, we'll do that Friday, and then Monday and Wednesday will be chapter 28. And we'll get to what we get to, and we won't what we don't, and you'll be done and off to the next thing. All right, so our goal at this point of glycolysis, recall we've already recouped our investment of ATP through substrate level phosphorylation. We converted an acyl phosphate into ATP. We've still got a phosphate group on 3-phosphoglycerate. The problem is it's a phosphoester. You want to hit what? I'm circling things and you can't see anything, right? Ah, well, sucks to be you. Sorry. And no, still no? Okay. Better? All right. So you got a phosphoester in 3-phosphoglycerate. And if we want to make ATP, remember the bond in ATP that we're going to make is a phosphoanhydride bond. So that's uphill, and it's not going to happen readily from a phosphoester. So the remaining few steps of glycolysis are all about changing around the functional groups, changing where the phosphate group is so that it's energetically favorable to make ATP. So as I mentioned last time, the first thing that we're going to do is move the phosphoester from the C3 hydroxyl to the C2 hydroxyl. That's an enzyme called mutase. This step is reversible. I told you not to worry about the mechanism of it. It's known. It just involves intermediates that are a little bit weird, and it's maybe not worth the trouble. So we're going to skip it. What this does is it moves the phosphoester closer to the carboxylate. And so one of the things that you might be doing here is introducing a little bit of charge repulsion. The negatively charged phosphate group is close to the carboxylate. The next step is also pretty easy. We will do the mechanism for this step. And this involves starting with 2-phosphoglycerate, but we're going to do an elimination reaction or a dehydration reaction to lose the OH group. So the enzyme, which is called enolase, and this reaction is reversible too, we'll use a basic side chain in the enzyme active site to deprotonate the alpha carbon. Now, normally when we've done dehydration reactions, this is sort of like the dehydration reaction following the aldol reaction. Normally, OH is a terrible leaving group, so we wouldn't show an E2 type mechanism. We would probably show deprotonating to make an enolate first, and then the electrons kicking down and the leaving group leaving. In an enzyme active site, side chains help protonate groups as they leave so that they can be good leaving groups. So we're going to just draw this mechanism as simply as we can. Electrons kick down to form a pi bond between the alpha and the beta carbons. And then the leaving group is going to leave, and as it leaves, it's going to be protonated by an acidic side chain in the enzyme active site. A dehydration reaction, we basically lose water, and the product here is this. And this is called phosphoenol pyruvate. And to understand this name, you sort of have to know what pyruvate is. So just as an explanation, pyruvate is the 3-carbon carboxylic acid with a ketone on the alpha carbon. So that's pyruvate. It's an alpha keto acid. The enol of pyruvate would be this. Would be the enol form, right? So we would call that pyruvate enol. You would expect pyruvate enol to be higher in energy than pyruvate for the same reason we've always said enols are higher in energy than ketones. That's because carbon-carbon pi bonds are not as stable as carbon-oxygen pi bonds, owing to oxygen's larger electronegativity. So phosphoenol pyruvate is the phosphoester of the pyruvate enol. And now we're set up to do the phosphorylation reaction with ATP to generate, a phosphorylation reaction to generate ATP. And the reason we can do this is that the thing that's attached to the phosphoester is a decent leaving group. And it's hard to see why until you remember that the thing that leaves could, by proton transfer, become this more stable pyruvate form. So let me show you how that last reaction of glycolysis works. Here's, and this is very downhill in energy, it's irreversible. There's 3 irreversible steps in glycolysis, the first, the third, and the 10th. So here's phosphoenol pyruvate. And the enzyme that catalyzes this is called pyruvate kinase. It's named for the reverse reaction. You're going to use ADP, and then ATP is going to be the product, or be one of the things that is formed, and then the other product is going to be pyruvate. So basically, we're transferring this phosphate. This is going to become the gamma phosphate of ATP. So how does that happen? Because we've thought about a negatively charged oxygen as being kind of a terrible leaving group. And so it's thought that what happens first is that a proton in the enzyme, or an acidic group in the enzyme active site, will actually protonate the pi bond first. Now, if you were in 351 and going to do addition of an acid to an alkene, which of these 2 carbons, the alpha carbon, we'll call it carbon 2 or carbon 3, which of these 2 carbons do you think gets the proton? 3, and why? You want the positive charge to be on carbon 2 because carbon 2 has an oxygen with a lone pair on it, and that can stabilize the positive charge via resonance, right? We could draw a resonance structure in which the lone pair on the oxygen forms an oxygen carbon pi bond. That would put a positive formal charge on the oxygen. And now you can see what's over here is an excellent leaving group. It gets to leave as something that's neutral. So by protonating that alkene, we set ourselves up, or rather, it gets to leave as something that's neutral, at least on the atom that leaves. Okay? Before we protonate the alkene, if this whole group left, it would be negatively charged. But because we've protonated the alkene first, it gets to leave as neutral on that oxygen. So from this point on, it's basically a kinase type reaction. I'll abbreviate ADP like this. You must remember that the oxygen here is one of the negatively charged oxygens on the beta phosphoryl group of ADP. That will attack the phosphorus. We're going to do what we've done before for kinases, generating a pentavalent intermediate. In which the phosphorus is attached to 5 things. Then electrons on one of the oxygens will kick down and kick off pyruvate, and that generates ATP. And as I said, that's downhill in energy, which gives you a sense for how high up in energy this phosphoenol pyruvate must be. And the reason that it's high in energy, as we've said, is first, you've got charge repulsion between the carboxylate and the phosphate that gets relieved when the phosphate is removed from the substrate. The other thing is the fact that the leaving group gets protonated by the enzyme so that it can leave as neutral, so it can leave as pyruvate rather than the enolate. Okay, so that's it for glycolysis. Yes?
Is it possible for the phosphate group to leave first, though? Or is that just like...
Possible for the phosphate group to leave first. I've drawn the mechanism multiple ways over the years. Some people try to draw all of this. Some people draw ADP attacking the phosphate at the same time as these electrons kick down, and then you get protonated all in the same step. I think that's probably fine. I'm showing this because it shows a pentavalent phosphorus intermediate, which seems to be the way kinases work, but I certainly don't have any problems with ADP attacking the phosphorus and these electrons kicking down all in one step. I've certainly seen people draw it before that way too. Okay, good. Others? All right, so there ends glycolysis. Pyruvate is, if you look at where we are, we've now, just to sort of summarize the overall yield of a molecule of glucose, in going from glucose to pyruvate, overall, the balanced equation has us using 2 molecules of ADP and 2 molecules of inorganic phosphate to generate, also, let's see, 2 molecules of NAD plus to generate 2 molecules of ATP and 2 molecules of NADH. And I guess we'll add the proton, though that's kind of silly. All right, so we've still got, I'm sorry, I should have put 2 molecules of pyruvate there. Glucose started with 6 carbons. All 6 carbons are still in our 2 3-carbon pyruvates. And we've generated 2 molecules of ATP, and for every 2 of NADH, we get, I think, 2.5 molecules of ATP in the electron transport chain. Sometimes, so that's sort of where we stop for anaerobic respiration. Sometimes if your body needs to, so NADH can go to the electron transport chain and donate its hydrides and regenerate NAD+. But under somewhat anaerobic conditions, if you're not breathing in enough oxygen, if your muscles are working really hard, you end up with an excess of NADH, and you need to regenerate NAD+. And so what your body will do is it will regenerate some NAD+ by taking some of the NADH that you made and reducing pyruvate to lactate. You've heard about lactic acid, and sometimes that's associated with muscle pain, and it usually eases pretty quickly because as soon as your body gets enough oxygen, it no longer needs to make lactate to recover NAD+. All right, so there's still a ton to be done. Ultimately, the CO2 you breathe out comes from these 3 carbons. But right now, they're not CO2. We've still got carbon-carbon bonds. This carbon is at the oxidation state of a carboxylic acid. It's got 3 bonds with oxygen. We need 4 to make CO2. This one's at the ketone oxidation state. It's got 2 carbon-oxygen bonds, but 2 carbon-carbon bonds that we're going to need to break and replace with oxygen. And then this one here, that one's at a pretty reduced state. That's a methyl group. It's got 4 bonds to either carbon or hydrogen, 0 bonds to oxygen. And so we're going to do a ton of oxidation to convert each of these into CO2. And as a result, we're going to generate a lot of NADH and some other things as well. So the process for doing that is, well, there's two sort of steps that cause this to happen. The first is called the pyruvate dehydrogenase complex. And this is going to convert pyruvate into acetyl-CoA. And overall, we're going to lose we're going to lose one of the carbons as CO2 for this to happen. So here's pyruvate. Oops. And this is sort of the bridge between glycolysis and the citric acid cycle. So you've got pyruvate here. You've got the pyruvate dehydrogenase complex. And basically, you're going to use NAD+. You're going to get a molecule of NADH out, and we're going to lose a proton along the way. You're also, so the enzyme is the pyruvate dehydrogenase complex. Along the way, you're also going to bring in coenzyme A, and you're also going to get out CO2. This carbon here and its oxygens are going to be lost as CO2. You're going to make the remaining two carbons are going to be acetyl-CoA. And then within the pyruvate dehydrogenase complex, there are some cofactors that are really important for making the process happen. And one of these cofactors is actually a vitamin. So thiamine is vitamin B1. And its structure is kind of complicated. I don't want you to memorize it, but you should be able to pick it up out of the lineup. It's got the most important part of thiamine is this 5-membered ring portion that contains both a nitrogen and a sulfur. There's a methyl group here. Nitrogen carbon pi bond there. This nitrogen's attached to something else that's positively charged. And the carbon that's in between the two of them is deprotonated. It's negatively charged. Over here, you've got a 2-carbon and then an alcohol and then a pyrophosphate group, which we'll abbreviate as we've done previously for pyrophosphate groups. And then here on the nitrogen, you have another weird aromatic ring. It almost looks like part of a nucleobase. This part of the molecule is not directly involved in the chemistry, so we won't worry about it. But that's thiamine, so that's cofactor 1. Second cofactor is called lipoate. This is also kind of weird. It's got a 5-membered ring with a disulfide in it, and then a hydrocarbon chain with a carboxylate group that's attached to the nitrogen, the epsilon nitrogen of a lysine side chain. So this is the alpha carbon of a lysine side chain in the pyruvate dehydrogenase complex. Okay, I know you're wanting it to stop, but nature's complicated. We're going to see it like it is, not like we'd like it to be. The other cofactor is FAD, and you've seen that before. All right, so that's FAD. You need all 3 of those cofactors for this reaction to happen. And it turns out the pyruvate, it's called the pyruvate dehydrogenase complex because it does 3 things. First, we've got to take care of getting rid of CO2. That's the sort of decarboxylation portion of the reaction. The second thing we have to do is convert these two carbons on pyruvate into the thioester. And as we do that, we have to oxidize this carbon from being a ketone to being a thioester. So I'll show you each of those steps. Hang on for the ride. We're going to pay, and what you learn here is going to be useful for a step in the citric acid cycle. Okay, so question for you. We've talked about decarboxylations before. There is a particular arrangement of atoms that undergoes decarboxylation really easily and spontaneously. What is it? We learned about it after when we did the malonic ester synthesis and we did PLP-based decarboxylation. If you want to lose CO2, you need something at which carbon? Okay, go look it up because that might be important to you in your future. Remember beta keto acids? Do you remember that pattern? The idea for decarboxylation of beta keto acids is that in a beta keto acid, if the negative charge on the oxygen kicks down, all of this is not a super great leaving group, but it's a decent leaving group because what leaves is a resonance stabilized enolate, which can then pick up a proton, right? So you need the ketone at the beta carbon to stabilize the negative charge on the alpha carbon by resonance. Unfortunately, pyruvate is not a beta keto acid. Pyruvate is an alpha keto acid, which means we don't really have the setup of functional groups necessary to do the decarboxylation. That's where the thiamine cofactor comes in. So let's go through the mechanism in detail. So the first step in the pyruvate decarboxylation complex is what I'm going to call oxidative, let's call it decarboxylation of pyruvate. So what's the role of thiamine? Let's draw just the portion of thiamine that's going to be important. And that's this 5-membered ring. The nitrogen's attached to an R group. There's a methyl group right by the sulfur. Nope, there's a methyl group right by the nitrogen, and then there's another R group by the sulfur. And the nitrogen has a positive formal charge, and then the adjacent carbon is deprotonated. So this thiamine is a decent nucleophile because it's got a negatively charged carbon. So that nucleophile will attack the pi star on the ketone and generate a tetrahedral intermediate. Some people will probably show that tetrahedral intermediate getting protonated. I'm not necessarily, let's go ahead and do. So one of the ways that enzymes work is they protonate tetrahedral intermediates to make it so it's easier to get to the intermediate, avoid having a buildup of negative charge. So the intermediate should have, and we'll have the carboxylate group here. And then here is the new bond that we made to thymine. We made it to that carbon that's in the middle between the sulfur and the nitrogen. Okay. So now look at what that was a nucleophilic addition reaction. Nucleophilic addition to a ketone. Here is the nucleophile, and here's what used to be the ketone oxygen. I want you to notice what's changed. Think about losing CO2 and look and see whether if we did the decarboxylation, if we did the decarboxylation, where would these electrons go? They go right on this carbon. How does the presence of the thiamine change things? Would those, if we broke this bond, would it be stabilized by resonance now? Yes, because of the pi bond in the thiamine ring. Just so you can see the pattern, let's look here. Carbonyl carbon, alpha carbon, beta carbon. That's not a ketone, but it does have a pi bond. So by having thiamine attack at the ketone, we install a group that can stabilize a negative charge by resonance. We put someplace for the electrons to go. Thiamine basically acts like an electron sink for the electrons that are going to come off and be left behind when CO2 leaves. So at this point, we're ready for a decarboxylation. I'll show you, so we lose CO2, and what's left behind, we could put a lone pair on that alpha carbon, what used to be the alpha carbon. I'll still label it as alpha. This is beta. Here's the nitrogen of the thiamine ring. Here's the sulfur. Positive formal charge on the nitrogen. Do you see how this is now stabilized by resonance? We can draw an alternative resonance structure that looks like this, where the negative charge, the lone pair associated with the negative charge on that carbon, is actually out on the nitrogen. To get there, all we have to do is move these electrons over to form a pi bond and then move the electrons in the pi bond onto the nitrogen. All right? So the presence of the thiamine stabilizes the negative charge that's left behind when CO2 leaves. So that's the decarboxylation step. Then I'm going to copy this intermediate. No. Sorry. I'm going to copy that intermediate because I want to continue leaving these arrows here to show you how to get to this resonance structure. But yeah, the point is that the leaving group is resonance stabilized. Okay. But as you can see, it's nucleophilic still on that, what we used to call the alpha carbon. And so what happens now is that five-membered ring, that weird five-membered ring containing disulfide, and I'm just going to write lysine here. The negative charge on what used to be my ketone carbon is going to attack one of the sulfurs, break the sulfur-sulfur bond, and then the other sulfur is going to leave, picking up a proton from some enzyme-linked acidic group. So here is a new carbon-sulfur bond that we just made. And then over here is the rest of the thymine molecule. And at this stage, we're ready to get rid of the thiamine. It was a nucleophile. We're going to kick it off as a leaving group. And you will see when we do that, that regenerates thymine. So So that's now released and ready to go. But what we have on the other side is this weird looking now thioester. And so if you look at overall what we've done, this is an oxidative decarboxylation because we started with a ketone and we now have a thioester. We've gone up a level in oxidation. We've increased the number of carbon heteroatom bonds. So my question to you is, if the carbon that used to be the ketone got oxidized, what got reduced? Can you find evidence for reduction anywhere? Redox reactions happen together. You can't oxidize one thing without reducing another. Reduction is either a decrease in the number of heteroatom bonds or an increase in the number of bonds with hydrogen. So can you find anything there that got a new bond to carbon or hydrogen? Go ahead. Yeah, lipoate, the disulfide there. A disulfide is an oxidized form. There used to be a sulfur-sulfur bond. Over here in the product, what used to be a sulfur-sulfur bond now has a sulfur-hydrogen bond on one side and a sulfur-carbon bond on the other side. So that is a reduction. So in this process, lipoate, which is oxidized, gets reduced, and then the ketone now gets oxidized, right? So it's the disulfide in lipoate that actually oxidizes the ketone up to the level of carboxylic acid, or up to the level of thioester. Okay, questions about that? That's probably the most complicated of the pyruvate dehydrogenase complex. The point is that thiamine allows you to decarboxylate an alpha keto acid by temporarily installing an electron sink for the electrons to go. Other questions? Okay, next step is easy. You've got one thioester, and we need to convert it to another. So the next step is called trans-thioesterification. That means converting one thioester to another, and the mechanism here is simply nucleophilic acyl substitution. So we probably don't need to show this one because you could probably come up with it on your own. Here is the, let's see. Here's the thioester from lipoate. And we're going to bring in acetyl-CoA as a nucleophile. A base will deprotonate acetyl-CoA. It will attack the carbonyl carbon of the thioester. You'll get a tetrahedral intermediate. And then the leaving group, and then the negatively charged tetrahedral intermediate will kick off lipoate and leave acetyl-CoA, or leave CoA in its place. The leaving group here will be the reduced lipoate. And though we won't draw that whole mechanism, I'll at least draw for you the tetrahedral intermediate so that you have an idea of what this is going to look like. I'm abbreviating the thiol of lipoate. Oops, wrong one leaving, huh? There we go. Okay, So, and the whole point of this, why bother changing thioesters? Remember, lipoate is permanently attached to the enzyme. So we want the thioester, but we can't have it permanently attached to the enzyme, so we're bringing in coenzyme A to liberate the acetyl group from the enzyme so it can go to the citric acid cycle. Okay, so there we've got acetyl-CoA and okay, the last thing we have to do is reoxidize lipoate. And that's a dehydrogenase reaction. The mechanism of this is actually more complicated than you would expect, and it's kind of fun. I printed it out thinking maybe we'd go over it. I think probably we won't, because it's not the most important thing, and I'd rather talk about the citric acid cycle. If you want to see it, it's perhaps more complicated than you would think, and in some ways it's, oops, too many carbons. In some ways it's kind of cool. But we'll just draw what the starting materials and products are, and we won't worry about this mechanism. So basically you're using NAD+, and to remake the disulfide in lipoate, you need to lose a hydride and a proton. So you could think about this as the hydride and this as the proton, or vice versa. But we're basically removing hydrogen, and that will remake oxidized lipoate that has the disulfide bond between the two sulfurs. I'm just going to put R here to make it easier to draw. It turns out, though, that you also need FAD, which is actually attached to the enzyme as sort of a prosthetic group to mediate this process. And how it happens, that's where the details get a little bit messy and more unfamiliar, and I think it's probably just beyond the scope of the class. So as long as you understand that we eventually use NAD+ to reoxidize lipoate, and then the enzyme's ready to go again, that should be enough. All right, questions about that pyruvate dehydrogenase complex? Okay, I want you to remember it because we're going to come upon a step in the citric acid cycle where we're also going to have an alpha keto acid, and we're going to use almost identical machinery, cofactors and all, to do that decarboxylation in the citric acid cycle. All right, well, we're ready. Forge ahead. We got, like, I don't know, depending on how you count, 8 to 10 steps of the citric acid cycle as well. All right, your goal in the citric acid cycle is going to be to take the thioester, and we want to oxidize it to 2 CO2s, okay? And look at what you've got to do. In the thioester, we're already sort of close to there in the sense that we've got 3 bonds to a heteroatom, but the methyl group, not even close. And so we need 1 new heteroatom bond here and 4 new heteroatom bonds at the methyl group. And so this CO2 is the CO2 that you were exhaling. So how does this happen? And it turns out that nature uses a really elegant way to do this. It's going to incorporate acetyl-CoA into an existing molecule where it's much easier to manipulate the functional groups and lose CO2. The interesting thing is, as soon as we incorporate this acetyl-CoA into the citric acid cycle, you were totally going to lose track of the carbons that were part of acetyl-CoA and the carbons that were part of the starting material. And it doesn't matter, because as the citric acid cycle turns, eventually every carbon you put in from acetyl-CoA gets released as CO2. We won't worry about tracking those carbons through the process. All right, so step 1 involves a step catalyzed by a molecule called citrate synthase. And you're going to take acetyl-CoA, and then you're going to take a starting material that's already present in the citric acid cycle, and it's called oxaloacetate. And it's a 4-carbon chain. Oxaloacetate is an alpha keto acid, 1, 2, 3, 4 carbons. Citrate synthase is going to incorporate acetyl-CoA into oxaloacetate, and what you're going to end up with is a 6-carbon chain that looks like this. Oops. Yep, on that carbon is an OH group, and on this carbon is a carboxylate. And this is called citrate or citric acid. So that's why this is called the citric acid cycle. The mechanism of this reaction, if you look at what's going on here, you have a ketone that's an electrophile, a carbonyl carbon, and an oxygen. This oxygen in citrate used to be the carbonyl oxygen. This used to be the carbonyl carbon. Here is the new bond that you made in citrate. That looks like an that looks like a beta hydroxycarbonyl compound. And so you would be right to suspect that this is an aldol reaction where we make an enolate out of acetyl-CoA, and then it attacks. The question is, where does CoA go? And it is released in a subsequent thioester hydrolysis reaction. You expect this reaction to be very downhill in energy because you're taking something that's a thioester at level 1 reactivity, and you're going to convert it into a carboxylate, which is level 4. So it's quite downhill in energy. So here's the mechanism. You would show a base from an enzyme removing the proton from the alpha carbon of acetyl-CoA. Now in a regular aldol reaction, we would draw the enolate as an intermediate. Instead, we're just going to show it attacking directly on the carbonyl carbon, and we'll show the resulting tetrahedral intermediate getting protonated by the enzyme all in the same step. So that's going to generate your intermediate. With the carbonyl, what used to be the carbonyl oxygen, the ketone there. Here's your new bond, and these are the 2 carbons of acetyl-CoA. All right, so that's the aldol step. Next is thioester hydrolysis, and this is just nucleophilic acyl substitution. So you expect a basic group in the enzyme active site to remove a proton, then hydroxide attacks the carbonyl carbon of the thioester. Then you expect electrons to kick down and kick off the better leaving group, which is the coenzyme A thiol. Electrons kick down, coenzyme A thiol leaves, and then that thiolate will deprotonate the resulting carboxylic acid to give you citrate. I'm not going to show that last proton transfer step. I think you can imagine it, and you could draw it if I asked you to, but I think that's good enough. So that's the thioester hydrolysis just by nucleophilic acyl substitution. Notice that citrate is not chiral. Notice that this arm is identical to this arm. So at that point, you totally lose track of which one was acetyl-CoA and which one wasn't. We just know that we've got two extra carbons in there somewhere. Okay, now, one of our stated goals of the citric acid cycle is to lose CO2. The challenge, of course, is, and we know two ways to do that now. You can lose CO2 by decarboxylation, spontaneous decarboxylation of a beta keto acid. And then we also know that alpha keto acids work okay as well, as long as you've got a dehydrogenase complex with thiamine that can make the process happen. The challenge with citrate is we got plenty of carboxylates, but we got no ketones. And the other problem is this oxygen, we could oxidize that to a ketone except for what? What's the problem there with that oxygen? It's a tertiary alcohol. There's no hydride to be removed. There's no oxidation that can happen. Okay, so that's kind of a problem. So the next steps of the citric acid cycle make chemical sense, chemically logical, because we want to manipulate where that OH group is so that we can oxidize it to a ketone. So the first step, the first thing after this is to, oops, no, that's fine. All right, so step 2 is going to involve citrate, and we're actually going to eliminate that tertiary hydroxyl group. And we're going to do it via basically a dehydration mechanism, similar to what we've seen after an aldol reaction. The enzyme that catalyzes this mechanism is called, this reaction is called aconitase. And a base deprotonates to generate an enolate, then electrons kick down, kicking off OH minus, but it doesn't have to leave as OH minus because it gets protonated as it leaves. This is basically a dehydration reaction. And the intermediate, or the product of this dehydration reaction, is what's called cis-aconitate, in which you've got an alkene. Here's the new pi bond we just formed in this process. You've got an alkene in between two carboxylic acids. And the product is called aconitate. Now, the interesting thing about aconitate is that this is a doubly alpha-beta unsaturated carbonyl compound. From the perspective of the blue carbonyl carbon, this is the beta carbon, and from the perspective of the pink carbonyl carbon, that's the beta carbon. Okay? Now, what do you know about alpha-beta unsaturated carbonyl compounds? Well, you know that they're aldol products, but you know that they're also electrophiles, and they're electrophilic at the beta carbon in addition to the carbonyl carbon. So it turns out by doing the elimination, we've set ourselves up for water to come back in as a nucleophile and attack the pink beta carbon instead of the blue beta carbon. If we attack at the pink beta carbon, we can move the oxygen over. All right, that's enough for today. We'll finish this next time.